Hello and welcome to Algebra 2, Big Ideas, Section 4.1, which is an introduction to polynomial functions and their graphs. We're going to start with some vocabulary so that we can all be on the same page and understand what the problems are asking you for. So the first vocabulary word that we've got is a term. A term is a mathematical expression. It can be a collection of factors, and it is separated by a plus or minus sign. So that's how you know when you're starting a new term, is that all of the terms would be separated if you have a plus or a minus sign. Then an expression that has one term is called a monomial. Makes sense because the prefix mono means one. Think about a monorail, or if a company has a monopoly on something. Those all come from the same prefix. A two-term expression is, you guessed it, a binomial, just like a bicycle has two wheels. A three-term expression is a trinomial. You've heard these words before when we were factoring. We talked about factoring trinomials or factoring binomials. And then this one is a little bit confusing sometimes. A polynomial, the prefix poly generally means many, and so some people would think that that is 4 or more terms, but it's actually 1 or more terms. So even if I have a monomial, I can still call that a polynomial. The polynomial is kind of the generic overarching word that we can use for no matter how many terms it would have. The next one is the degree of the polynomial. The degree is the highest variable's exponent in the polynomial. Now, if the polynomial has multiple variables that are being multiplied together, then this definition is not quite the same thing. But for polynomials, which is what we're working with right now, it's going to be the highest exponent that's on a variable in the polynomial. That would be whatever the degree is. Standard form, again, this is not an official definition, it's just kind of a working definition. Standard form for a polynomial would be to put the terms in order by decreasing exponent, which is what you're used to seeing for linear functions and for quadratic functions. So that's the typical standard form. Then we have the leading term of the polynomial. The leading term is the term that contains the highest variable exponent. So when you're looking for that highest variable exponent to find the degree, when you find it, that entire term is called the leading term, even if it's not the first term that is written in the polynomial. The leading term will be the first term if your polynomial is written in standard form, because then the highest exponent is first. And then lastly, the leading coefficient. So the leading coefficient is just the coefficient of the leading term. And we'll do some examples here in a bit. We also want to make sure that you're familiar with this notation here about this x and then the arrow and then infinity, or the x and then the arrow and then negative infinity. So this would mean as x approaches negative infinity, which indicates that you're going to the left. Because if you think on a number line, the x on a number line is the horizontal, and as x goes to negative infinity would be that way if we could reach it. The other one is as x approaches positive infinity, or you can just say infinity. And that means you're looking all the way on the graph to the right. All right, if we could get to positive infinity, we would have to go right and right and right and right and right to get there. We know that, of course, we're never actually going to be able to get there. So those are your vocabulary words for the day. Let's do some examples to make sure that you understand what those mean. So first we have name by the degree and the number of terms. So if I write 10x to the third power, then I would look at the degree, and I would say the degree is the highest exponent, which in this case is the only one, which is 3. So this is a third degree. And then I also have to name it by the number of terms. This is only one term, so this is a third degree monomial. Let's look at another example. Let's say I have 5x to the 7th minus 2x plus 7. This would be a 7th degree, since 7 is the highest variable exponent. And then I have 3 terms here. Can you find them? One term would be 5x to the 7th. Then I would have one term that's 2x, or you can attach that minus sign onto it and think of it as negative 2x if you like. And then I'd have another term of 7. So there are 3 terms here, which means that this is a trinomial. Let's do one more. So if I say 4x minus 5x squared, then the highest degree is, or the highest exponent is 2, which is the degree then. So I can say a second degree. And there are 2 terms here, the 4x and the negative 5x squared. So this would be a second degree binomial. If we look and see if these are in standard form or not, the one term, the monomial one, is obviously in standard form. There's nothing to do with that. And the second example is also in standard form because the exponents go from 7 to 1, which is implied there, to 0, the constant term, you could think of this as 7x to the 0 power. So yes, that one is in standard form. This third example is not in standard form, so if I were asked to put it in standard form, I would have to rearrange the terms. So the negative 5x squared would have to go first since it has the highest exponent, and then the positive 4x would come next if I was switching that into standard form. Also, you may be thinking, why are we calling that second degree when we have called it something else in previous chapters? And you're right, that we have specific names for 1, 2, 3, the lower degrees. So instead of saying second degree, that's also known as quadratic. That if you have a quadratic function, then that indicates that that's second degree. Similarly, if you have a first degree function, I'll just stick it over here. If you have a first degree, then you can call that a linear function. And if you have a third degree, you can call that a cubic function. If you have a fourth degree, you can call that a quartic function. And they do, there are some others after that, but those are really the only ones that we would ever use. In fact, a lot of times we don't even use the quartic one, but you might see that in your calculator if you're going to create regression. So it's kind of nice to know that that exists. We also want to be able to describe the end behavior of a polynomial. The end behavior means as x goes way off to the left or as x goes way off to the right, what happens to y? And so when we say end behavior, it's automatically asking 2 questions that are implied, both as x goes to the left, which is negative infinity, and as x goes to the right, which is positive infinity. So this can also be written as the limit as x approaches negative infinity of f of x. And this one can be written as the limit as x approaches positive infinity of f of x. So this part is the part that says that x is either going to the left or x is going to the right. And f of x just says that we want where is the y value going, since we know that f of x is the same as y for our purposes for this chapter. And the limit just means where is that headed, where is y headed. So we don't actually say y is going anywhere when we use this notation. The limit is already indicating that we're looking at where it's headed, so we just say equals, and then we would say what number it equals. As x goes to the left, this is called the left end behavior. Go figure, right? And as x goes to the right, or positive infinity, that's called your right end behavior. And you'll see me abbreviate these with just LEB and REB when we would talk about them. So here are some examples of functions that we should be able to describe their end behaviors. Let's look at this one. So in this first example, as we look to the left, we can see that the x is going to the left, and what is the y doing? The y is going up, and we would assume that the y is going to continue to go up from what this looks like, and so that would mean that the the left end behavior would be towards positive infinity. So I can say left end behavior as x approaches negative infinity, y approaches positive infinity. I can also then talk about the right end behavior. For the right end behavior, as x goes to the right, so we're thinking about going this way on the number line, right? As x goes to the right, y is going down. So as x approaches positive infinity, y approaches negative infinity. The first part here, all of this, is kind of the setup for the problem, which you can see from up here. So the answer to the problem is just telling me where y does approach as you're looking to the left or to the right. Let's do one more example of that. Look at something like this. For a function like this, and we'll use the other notation this time, the limit as x approaches negative infinity of f of x equals, well, let's think about it. As x approaches negative infinity, that means we're headed to the left on the graph. And what is y doing? Y is going down towards negative infinity. So I would say that this limit equals negative infinity. And if we want to finish that out, we can do the limit as x approaches positive infinity of f of x. And as x is going towards positive infinity, which is going to the right, what is the graph doing? The graph is still going down towards negative infinity. So in this case, the right-hand side of the equation, those negative infinities are indicating that that's what y is headed towards. There are some rules that we can use when we look at polynomials to determine what the end behavior of the polynomial is going to be without graphing it. So that's kind of nice. We need to look at two different things to be able to do this. The first is whether the leading coefficient is positive or negative, and then the second is the degree, odd or even. So if the leading coefficient is positive, then that indicates that the right end behavior is going to head towards positive infinity. If the leading coefficient is negative, then that indicates that the right end behavior of the function is going to go towards negative infinity. You can hopefully make sense of this in your head or wrap your brain around this if you'd like by thinking about substituting a very large number. You don't have to do that, but if you're not sure or if you forget what the rule is, you can think about substituting x equals 1,000 and then see what would happen if you need that extra help. So that determines, the leading coefficient determines our right end behavior. Then we look at the degree of the function. If the degree, which is that highest variable exponent, if the degree is odd, then that means that the end behaviors are different. So whatever the right end behavior was, the left end behavior is different from that. This makes sense because odd and different can be synonyms, right? If you know somebody who would be considered a little bit odd, it just means that they're different than other people. And if the degree is even, then that means that the end behaviors are the same. If you know someone that has an even temperament or even keeled, it means that their mood does not fluctuate a lot. It is consistent, or it is the same. So that might be a little bit of a stretch, but you can use that to help you remember perhaps. So in this nice little chart I'm about to make for you, we can kind of see whether the graph is going to tend up or down to the right or the left. Of course, we don't know what's going to happen in the middle of the function, so I'm just going to draw some arrows and leave the middle of the function blank. If the leading coefficient is positive, so that would be this row here, then I know that it goes up to the right. So I'm just going to draw like a up to the right in this box, and that's going to be the same whether or not the degree is odd or even. If the leading coefficient is negative, then I know that the right end behavior is down. So to the right of the graph is going to go down. So that's regardless of whether the degree is odd or even. And now I can look at the degree to finish and get the left-hand side. So if the degree is odd, then I know that the end behaviors are different. So in this first box, here, all right, we have down to the right, which means it would go up to the left. This is not a coordinate plane. I realize this perhaps looks like a coordinate plane. It's not. These are just 4 different boxes. Just a nice little graphic organizer for you. If the degree is odd and the function goes up to the right, that means it would have to go down to the left. So this is the second case that you're going to see here. If the degree is even, the end behaviors are the same. So that means that if the right end behavior is down, then so is the left. And if the right end behavior is up, then so is the left. What the function does in the middle, whether or not the function looks like this, which maybe might look like a cubic, or it might look like that, which could be a quadratic, but it could also wiggle back and forth several times before it decided to do something else. And so we don't really know what the function looks like in the middle. And so we don't actually put anything in the middle when we're just thinking about the end behavior, but it could be, these could be examples of what they would be. That's why I'm leaving the middles blank there. Next, we're going to talk about the vocabulary words of increasing and decreasing. So increasing just means that it's moving up as the graph goes from left to right. So actually, I don't even need axes. Increasing would be anything that is moving up as you look from left to right. You have to remember that you're always looking from left to right because that's in ascending order for x. That's how we read a book. We read words on a page. As long as you're reading in English, you're reading from left to right. And so that would be increasing, which means that it's moving up from left to right. Decreasing means that it's moving down, again, from left to right. So you've got to always remember to think about going left to right and not the other way around. For example, we've got this nice little cubic equation. Go ahead and if you have a graphing calculator, you can graph it. And then we're going to look and see what its end behaviors are. So I've gone ahead and graphed this one. I just used the Desmos website, so you can use that potentially if you don't have a graphing calculator. And we can see that the function is missing the arrows because Desmos won't put the arrows on the edges of our window. But it will locate that it looks like this point here is -1, 6, and this point down here is 3, -26. So we could see where is this graph increasing and where is this graph decreasing. The key word here is where is the graph increasing and decreasing, which means that we're looking for x intervals. generally the word what is going to refer to y, the y value of a function, and the word where refers to an x value of the function. So we're looking at x intervals. So I'm going to just start tracing the function from left to right, and we're going to see if it's increasing or decreasing. So as I start all the way to the left of my graph space, I can see that this is going up from left to right. Therefore, that must be increasing. That would be from x, would be all the way from negative infinity to the x value of -1. The 6 is the y value. I don't care about the y value when I'm talking about increasing, decreasing, because I want just the x interval since it was asked where is the function increasing, decreasing. Now I'm going to continue tracing. So from where I was, I'm going to keep going. Now the function is going down like a slide. So it would be decreasing from -1 to 3. Again, I'm only looking at the x values. And then if I continue tracing, now the function is going up again. So I would add that to my increasing intervals, that from 3 to infinity, the function would be increasing. When I finish, I should be able to make a nice little train of all of my intervals that should cover the real number line, the whole number line. So if you've accidentally done this with y's, then that probably won't work. It won't make sense. That can be a nice little check to yourself. If I was making it a little train, I could say, well, let's start at negative infinity, and then that would go to -1 here, and then from negative infinity to -1, then I have down here that from -1 to 3, I was decreasing, and then I would go from 3 to infinity and be increasing again. So it makes sense that I've got all of my numbers covered. Now I used open brackets, so I didn't actually cover the numbers, the x values of -1 and 3. Those would be where you would have a stationary point that is neither increasing nor decreasing, because it's either a maximum or a minimum, and so we don't include those points on the increasing, decreasing. The last thing that you might be asked to do in 4.1 is to sketch a graph with some properties given. So here's an example of that. We can sketch a graph that is increasing for all x values less than 0 and greater than 4, decreasing for all x values in between 0 and 4, and then it needs to go through 2, 2, and 0, 6. So let's start by putting the 2, 2 and the 0, 6 on the graph, because that's going to be the ones that are hard and fast that we have no wiggle room with. So let's go ahead and just locate those, 2, 2 and 0, 6. All right, so now let's plane out the roadmap. It says that it's increasing for all x's that are less than 0. So everything to the left of the y-axis has to be increasing. Then it has to be decreasing, but not only decreasing, but going through those points and then decreasing all the way until I get to this x value of 4 right here. And then it says that for all the x's bigger than 4, then it's increasing again. So this is an example of a graph that would meet those properties. Now, because it's not otherwise stated, we would assume that the domain is all real numbers, which means that we would want to put arrows on our graph. And we would want to make a nice, smooth, continuous function that doesn't have any breaks. So this is a continuous function, but I'm not sure how nice and smooth it is. All polynomials are going to be smooth and continuous. So now that I kind of have this roadmap idea, I can go ahead and say, all right, well now let's see if I can do something to make it smooth and continuous. And so I can just kind of eye that in smooth and continuously, and then ignore the, oh, sorry, I don't want to erase both, and then ignore the other guide line that I was using, right? I was just using the black line to kind of eye in whether or not I was increasing or decreasing. So there you go. There's Algebra 2 section 4.1. Good luck with your practice.